This is section 6.2, volumes, content objective 2, which is to find volumes of solids of revolution using the disk or washer method. Before we get into the nitty-gritty components of how we do these problems, I want you to be able to visualize the solids. And again, courtesy of Audrey Weeks and Calculus in Motion, we have something that can help us see what is going on when we revolve around an axis of revolution. The first thing you need to know is that when we create disks or washers, they come from having strips that are perpendicular to the axis of revolution. So it's like this blue strip right here. We have a blue sample strip in our region, and it's perpendicular to what we're rotating around. And when we revolve it, you can see that a disk with a hole cut out of it, or a washer, is created. So our goal is to create a whole series of these and then find the volumes of one sample slice so that we can add them all up in an integral. If we now think about an entire region where we have a curve and we are rotating around this axis of revolution, we have drawn a sample slice that is perpendicular to the axis of revolution so that when we revolve it, we get a disk. Notice that there's no hole in the center of this disk, and because there's no hole, we don't use the washers, we're actually going to use a disk. So this disk represents all of the disks that would fill the region. So when we integrate the volume of one of those sample slices, we get the volume of the entire shape. Now, something that's important to know is that this axis of revolution can either touch the region itself, or it can be somewhere else. So here, for example, we have the axis of revolution is 1 unit away from the boundary of the region, and when I revolve, we can see that having that axis of revolution separate will create a hole, and in this case we will have a washer. So we can again sweep that sample washer through the region and see that one of those sample slices will represent all of them. We can also have this axis of revolution be above the region as opposed to below. And this time when we revolve, we can see that the size of the hole is going to change. Again, as we sweep that disk and washer through, it represents the entire collection of washers. Well, how do we find that volume now that we can visualize the entire shape? Well, we've got some steps. This time there are 7, and some of them you should remember because we've seen them before. Our first is to graph all the boundaries. We've done that in both with areas and with our volumes of cross sections that are the same. We label the intersections. Again, that's a repeat of what we've done. Next, we're going to draw a representative strip, and this time we will have to draw it so that it is perpendicular to the axis of revolution. So they will tell us what the axis of revolution will be. It will either be an axis, so it would be the x-axis or the y-axis, or it will be a vertical or a horizontal line. So whatever that axis of revolution is, we will then create a strip that is perpendicular to it. And this time when we label, we're going to label both the endpoints of the strip and a concurrent point on the axis of revolution. So that means we're going to have a point that would be on the same line as the strip we have just drawn. And all 3 of those points will be labeled either with x if we're perpendicular to the x-axis, or with y if we're perpendicular to the y-axis. Once we have them labeled, we are going to use that strip to sketch a representative skinny 3D slice. It will either be a washer or it will be a disk. So if it's a disk, that happens when the strip for the entire region will be touching the axis of revolution. Or we'll write it as a washer if the strip, even once, does not touch the axis of revolution. Then we will use the labeled representative strip to determine the dimensions of that 3D slice. We're going to need a large radius and possibly a small radius if we have a hole. Then we'll write the volume of the skinny slice in terms of x or y using the disk formula, which is pi r squared times the thickness, or the washer formula, which is pi times the big radius squared minus the little radius squared times the thickness. So before we move forward, let's think about that step 6. If I have a washer and I'm trying to find the volume of that washer and I have just a hair of thickness, then we can see that the volume will be the big disk, which would be pi times the big radius squared times its thickness, which is d whatever, and then we will subtract out the little disk that was cut out of the middle, and that one would have a small radius. So that would be a pi times a small radius squared times the thickness. Notice if I factor the pi out and I factor the d whatever out, then we get this formula right here. So finally with step 7 we will just add up all of those integrals. And notice that we pull the pi out in front because a lot of times people mess up with parentheses and they'll only attach the pi to the big R instead of to both. So if you put it in front, you'll avoid that error. Looking at example 1 here, we want to find the volume of the solid formed when this region is bounded by the cosine of x and the x-axis from negative pi over 2 to pi over 2, and we want to revolve it about the x-axis. So our first step is to graph the region, which we've done, to label our intersections, and draw our representative strip. So our representative strip, since we are revolving about the x-axis, we want to be perpendicular to the x-axis. Once we've drawn the strip, we're going to label everything in terms of the axis we're perpendicular to. So in this case, the y-coordinate of this point, no matter where the strip is in the region, is going to be on that curve y equals 0. The top point, no matter where it is in the region, is going to be on this curve, which is the cosine of x. So our next step is we want to draw a representative slice after it's been revolved. When we do that, we see that since everywhere we could put that strip, we are touching the axis of revolution, we are not ever going to get any hole in the center. We're always going to have it touching. So we're actually just going to have a disk, and our goal is to write the volume of this one disk. So to write the volume of the disk, we need a pi times a radius squared times a thickness. Well, the thickness is a little bit of the x-axis, and the radius is going to be the length of this strip, which is the top y-coordinate minus the bottom y-coordinate, or just cosine of x. In order to get the volume of the entire region, we are going to add up all of those slice volumes and let x go from its lowest possible value to its highest possible value. Now bear in mind that we could have also used the symmetry of this graph and simply double what we get going from 0 to pi over 2. Now in this particular problem, I would not expect you to be able to do it analytically, so you can use your calculator to yield either pi squared over 2, which is the exact value, or the approximate decimal, which would be 4.934. With example 2 now, we are going to follow the steps, which is to graph the boundaries of the base, which we've done. We will label all the intersections, which we can see are negative 1, 0, 1, 0, and 0, 3. Then we'll draw a representative strip that is perpendicular to the axis of revolution, and we need to label its endpoints along with a concurrent point on the axis of revolution. Because we are perpendicular to the x-axis and the coordinate that is shared by all three of these points is an x, we're going to label everything using x's. This point has a y-coordinate that comes from the top curve, and the top curve is this one because it's got a vertex at 0, 3 as opposed to 0, 1. So we'll put a negative 3x squared plus 3, and then on this one we are on the second parabola, which is a negative x squared plus 1. And then our third and final point, which is on the axis of revolution, has a y-coordinate of 0. Now, when we now go to our next step, which is to use this strip to create a representative slice, we can see that this time we are going to get a washer that has a little bit of thickness to it. So in order to write the volume of this washer, I need to know the big radius and I need to know the little radius in addition to the thickness. The thickness will be the thickness of this strip, which is a little bit of x. The small radius will be the distance between this point and this point. So it's a vertical distance, which means that it'll be a top y-coordinate minus a bottom y-coordinate. This distance here will be the difference between this top y-coordinate here and the one on the axis of revolution. So my big radius will be a negative 3x squared plus a 3 minus a 0. Now that we've labeled all the parts and pieces, we can now set up the volume of that representative slice. It will be pi times the big radius squared minus the little radius squared, all times the thickness, which is dx. So in order to get the volume of the entire region, we need to sum up all of the slices volumes from the smallest x-coordinate to the largest x-coordinate as the strip moves through the region. We can see the smallest x-coordinate is a -1 and the largest x-coordinate is a +1. Now this particular problem you could use the fundamental theorem of calculus because you should be able to get the antiderivative of this. However, we will not take time right now to do the antiderivatives. I'll just let you put it into your calculator. To get 128 pi over 15. With example 3, again we are going to graph all boundaries of the base. So those boundaries are -x plus 2, y equals 0, and y equals -2x plus 2. So you can see that the steeper line is this one, whereas the shallower line that has a slope of -1 is this one. And we're going to rotate about the line x equals -1. So our second step is to label all the intersections. We can see here that's where 0, 2, 2, 0, and 1, 0. Step 3 is we want to draw a representative strip that is perpendicular to the axis of revolution. So because this is our axis of revolution, we are going to draw a line that is horizontal. We're also going to draw a point that is concurrent and on the axis of revolution. Notice that all three of these points share a y coordinate. So we will label the y coordinate for all three of them. We'll notice here that the x-coordinate needs to be in terms of y on this shallower curve. So we're going to solve for x and get 2 minus y. For this one, again, we'll be on the steeper curve, so we will need to isolate x on this one. We'll have y minus 2 equals -2x, and x will equal 2 minus y over 2. And our final point here, the x-coordinate always resides on this axis of revolution, which is -1. So when we now draw our representative slice, it will be a horizontal washer with a hair of thickness. Notice that the thickness this time will be a dy. The big radius is going to be the difference between this point and this one. So it'll be the right x-coordinate minus the left x-coordinate will be 2 minus y minus a -1. So that ends up being a 3 minus a y. The little radius, on the other hand, is going to be the difference between this point and this point. So it will be the right x-coordinate minus the left x-coordinate. So we have a 2 minus a y over a 2 minus a -1. We could, if we wanted, rewrite this as a 1 minus a y over 2 plus a 1, which would be a 2 minus a y over 2. Now that I have the parts and pieces, I can write the volume of that particular shape. It will be pi times the big radius, which was 3 minus y, squared, minus the little radius, which was 2 minus y over 2 squared. The thickness is dy. This now represents the volume of that one representative slice, and I will add all of them up, keeping in mind that the lowest y value I can get is a 0, and the highest y value I can get is a 2. Again, I will allow you to use your calculator for this, even though you could ideally use the fundamental theorem of calculus to simplify. To get 4 pi.